Hi again, everyone, and thank you for joining us for this keynote and industry session of Day 3. First of all, I would like to introduce you to this session's chairman, Yannick Villemont from 90 Labs. Yannick is into innovation and technology topics with deep experience in the composite and advanced materials field. He has both an engineering degree in mechanics and an MBA in entrepreneurship. During his 13 years at SGL Carbon, he acquired both composites and managerial competencies through his roles in R&D, sales, procurement, and innovation strategy. In January 2020, he joined 90 Labs as a business development specialist. Yannick, the stage is yours.
Thank you, Cécile. Dear participants, it's a great pleasure for me to moderate the last session of the JEC Sports and Health Summit 2020. While the two first days focused on current trends and innovation, we will now have a look at challenges and opportunities to better understand the increased use of composites in future applications. Some housekeeping here, so the Q&A will take place at the end of the session at 5 p.m. Please feel free to share any question already during the presentations in the Questions tab on the right of your screen. And you also have the possibility to upvote the questions. Of course, we'll try to answer most of the questions as soon as we have them, if we have enough time. All other questions will be answered in written form afterward. So to launch the session, I'm glad to welcome Damiano Salvatori from Straumann Group. The Straumann Group is based in Switzerland, Basel, with a focus on the whole value chain for clear aligners in the dentistry field. So including both soft and hardware. The group began as a family-owned institute and grew into a publicly owned holding with a global footprint nowadays. So Damiano, he's a material scientist and owns a PhD in thermoplastic composites processing from the Swiss Federal Institute of Technology, also called EPFL in Lausanne. In his current position as subject matter expert on polymeric materials and plastic-based medical devices, Damiano is active through the whole R&D process. Means it ranges from pre-project activities, screening and evaluating new materials, techs, and partners, to the support for medical device registration. Damiano, the stage is yours.
Thank you, Yannick, for this introduction of myself and of the company. I would like to start with a question, and you have a few seconds to answer in the question tab. What do you think it is, the one high-volume industry that is it's pioneering the use of additive manufacturing technologies in terms of volume? So you might guess it has to do with the dental industry, coming from Straumann Group, but more specifically, it's this device here that it's called a clear aligner. And as I said, it's probably the one application, the one product which has the highest volume, including the 3D printing technologies in its manufacturing process. But I will come back to this in the second part of the presentation. And I will start first with an introduction to the Straumann Group and focusing a bit, giving an overview on our products, especially those making use of polymers and composites. And then the second part, I will focus on clear aligners, which is more my field of expertise, how they work, how they're made, and what are the material requirements, and what are the opportunities and challenges for composite materials, and also for photopolymer resins. So the Straumann Group started as an Institute Straumann. As Yannick already said, it used to be a research institute, then evolved into an implant manufacturer and provider, and it was still so until 2012. And afterwards, in the last few years, it was revolutionized into a total solution provider for aesthetic dentistry. So we are based in Basel, in Switzerland, but our presence is worldwide, crossing different brands across different countries and on different sectors, not just dental implants, but also prosthetics and orthodontic solution, biomaterials, but also partnering and shares in technology brands, especially in the digital workflow, in particular 3D printing, and resin manufacturers and thermoplastic manufacturers. So I mentioned the digital workflow. This is crucial for us. For us, it's the present and future, and for many others, it will be the future of dental practice. The digital workflow goes from the data acquisition through the planning, surgery, but also components design, product design, and production. This gives an overview of our products. So as you can imagine, the digital workflow has the advantage of a customized product, but still to be produced in volumes. So for us, it's critical. And so this is an overview of our products. So not only dental implants, mainly made of metal. We also have biomaterials for bone annealing. And then we have also metal prosthetics and ceramic crowns and bars and bridges. So as far as polymer and composites are concerned, it's mainly crowns and bars and bridges, some smaller components, and also clear aligners. So what are the requirements for dental materials? They are more or less, in a way, they share some requirements with many other medical devices. They have to be performant, depending on the specific application. They have to be tough and resistant to different types of loading, and notably cyclic loading, and also resistance to fracture toughness, to fracture rupture. So fracture toughness requirement. They have to be chemically stable in the intraoral environment, which can be quite a harsh environment. Also, they have to be safe in terms of biocompatibility and comfort also for the patient. They have to be durable, with a durability that can range from a few minutes to several decades. And the one requirement that's probably differentiated the dental materials from others is the aesthetic, because I bet that unless you are a pirate, you don't want to look like this. So ideally, some of you might like it, but normally the average person wants their restorations, for example, to look as close as possible to the neighbor's teeth, both in terms of shape and of color. So I mentioned restorations. They are small components, or can cover one or more teeth. So they can be actually quite large, and they're meant to replace partially or totally the external part, the visible part of the teeth. They are mostly produced by subtractive manufacturing, starting from by milling, starting from blocks or discs of material. And here's an overview of some materials in our offering. The highest performance are ceramics and glass ceramics, and also metals, but we do include some polymers and composites. So as far as polymers and composites are concerned, we can classify them depending on their durability. These are three major of our products. For short-term crowns, we have a PMMA-based polymer. This has the advantage of being produced chairside. It's a cheap solution for an immediate production in the same dental practice or in dental lab, and they have a durability of few days or weeks. And for still temporary, but for midterm durability up to 3 years, the reinforcement of metacrylate resins with little amount of microfillers, microparticles, it's enough to improve its durability, improving the strength and the elastic modulus. And then for final restorations, so for long term, and also covering a large number of teeth, even a whole dentition. The choice is a PEEK, which combines the high strength mechanical properties to a low density, which makes it desirable for its lightweight, because it has to do with large. It's a large product. It's a large device. It would literally make the jaws drop. Another high-end offering for final restorations, it's a kind of composite. We like to call it more a hybrid, actually, because it's not a particle field reinforced resin. It's from material science point of view, for me, it's still a composite. It's basically a ceramic network infused with a polymer resin. So this gives properties a bit closer to a ceramic in terms of modulus of elasticity, abrasion resistance, and also aesthetic. But combined with the polymer network, we have a tough material, resilient material, also with a bit lower modulus of elasticity, which matches more nicely a real tooth. When it comes to additive manufacturing, here's an overview of the different products. They're all methacrylate-based resins for DLP printing. The advantage of additive manufacturing is that they can be produced, well, first of all, it's less material used, and they can be produced quite quickly also in the lab. So it ranges from orthodontic to crowns and bridges, bite splints, surgical guides, gingiva masks, and dentures. Crowns and bridges, in this case, are rather temporary solutions than final solutions. And as you can see, there are no clear aligners, although I started this presentation talking about clear aligners and 3D printing. I'll come to that. They're not directly produced via 3D printing, but I'll come to that in the next slides. So first of all, what are clear aligners? So it's a removable and transparent orthodontic appliance. So it is meant to replace traditional brackets and braces for teeth alignment. And with they offer improved aesthetic. They are much more discreet, and also comfort, as well as hygiene, being easily removable for eating food and for oral hygiene. They work based on the well-known orthodontic principles. So by application of a constant gentle force on the crown of the tooth, they activate the biology in the root, specifically the osteoclasts and osteoblasts, which are cells that break down bone and build up the bone, respectively. And so they break down bone in the points of compression, and the osteoclasts, and the osteoblasts, they build up fresh bone in the points of tension. And this way, it results in a net movement of the tooth over a long period. So how it works with aligners, basically there's a number of steps. The patient receives a number of different aligners, not just 4 as in this picture, but it's more 20 or 30 aligners, and they are planned to every aligner, which is changed after 1 or 2 weeks, depending on the case. This aligner moves the teeth. Every aligner moves the teeth a bit further until the final position is achieved. So everything starts. So here as well, it's all based on digital workflow. Everything starts with an intraoral scan to take an impression, a digital impression of the patient anatomy. This is then transferred into our digital platform, where our technicians create the treatment plan. And so they create the final position of the teeth, and then the software creates a number of steps in between, intermediate steps. And for each step, we 3D print a model, and that's where the 3D printing it really makes a difference. and where it is employed largely. So for each model corresponds a treatment step, and then each model it's used as a mold for the thermoforming of the actual aligner. And then there's the trimming out of the plastic sheet, and some polishing, and then it is delivered to the patients. So when it comes to specific requirements for the clear aligners, so one requirement is that they should deform ideally only elastically. Otherwise, they would deform. They shouldn't deform permanently, especially when they are inserted or removed from the mouth. They should apply a constant moderate force or stress, and they have to fit accurately in the mouth. They have to be also tough and strong, chemically stable in the intraoral environment, biocompatible and comfortable and safe, generally speaking. They have to be durable, and it is normally a couple of weeks, but in some cases it can be up to 6 months, especially for the last aligner. And for the aesthetic, they have to be resistant to staining from foodstuff like coffee. It's a highly staining agent, or mustard also. And they have to be transparent and discreet and not visible at a talking distance. So these are translated into material requirements, as shown here. For example, quasi-static properties like tensile and bending. They should have a large enough elastic range, so minimum yield strain of 4% and stress of 30 megapascal. And they have to also have a higher strength. And one property which is really crucial is the ability to retain stress or stress retention. So polymers are viscoelastic materials. They tend to flow under a constant applied deformation. They tend to relax the stress. Which is not exactly what we don't want, because we want to apply a constant stress over time. So this means that if you have a drop of 70% in 2 days, you have to start from a quite high initial stress in order to still have a certain amount of stress applied for the treatment. Flexural fatigue is another requirement. They have to undergo several cycles. So in the patient's mouth, they are subject to involuntary chewing, and then they are removed. And by the way, I can show you one. I have it here. So they are removed from the mouth, and doing so, every time they are somehow deformed. So they have to have some flexural fatigue resistance and also fracture toughness and tear resistance. Other requirements are water absorption should be quite low, because the mouth is quite a moist environment. Dimensional accuracy and stability, because they apply the movements in place are really small. We're talking about 0.3 millimeters for translation and 3 degrees for rotations. So that it should be accurate enough. And then, as already mentioned, staining resistance and high transparency. So here are some examples of state-of-the-art materials, although not top of the class. But the mostly used materials are polyethylene terephthalate, normal and glycol modified, especially glycol modified, thermoplastic polyurethane, polycarbonate, and polypropylene. So these are thermoplastic sheets of thickness 0.5 to 1.5 millimeters, and are used for thermoforming, as I showed before. As I already mentioned, stress relaxation is a big problem, and for this material, it is a problem. So they work, although there is a high stress relaxation, but we have to start from a quite high applied stress, which makes the whole device quite stiff, relatively stiff compared to traditional bracket and braces, but still can be quite stiff and can result in discomfort for the patient. So the solution for us and for now the major actors in the industry is to combine different materials, and that's where finally composite come into play. Although it's not really a composite in the general sense. It does combine two materials, which are copolyester thermoplastic as the two skins of the sandwich, which provides a barrier against staining media and also against water. It provides a certain structural rigidity and also resistance to grinding, and provides adaptation. And in the middle, there's an elastomeric core, thermoplastic polyurethane. And this provides a certain flexibility, which is good for the comfort, and also a high ability to retain the stress. So I'd like to show you here an example of our flexural stress relaxation test we did in our lab. So it's a 3-point bending, a constant deflection, 2% and in water at 37 degrees. Our 3-layer material, as you can see, starts from a quite lower initial stress, but it's over time, it's more sustained compared to an example of a polyurethane and a PETG. So the lower initial stress means it's associated to a higher comfort, and the more sustained stress with a more predictable, a more constant force application. And as you can see, in terms of tensile properties, for example, the three materials, the 3-layer material, it's a bit softer and also a bit less strong, which means indeed we are not using this for longer than a few weeks or a couple of months, compared to the other two that can also be used as final retainers, meaning that they can be in the mouth for 6 months or more. So I would like to conclude with the next 2 slides, showing a bit what are, from my point of view, the opportunities and challenges for other materials, in particular composites. As you have seen, this 3-layer material, it's a result of 2 different layers that combine more stiff and a more soft material. This is the option that the industry, the market, is adopting, us and other actors with these and other configurations. I don't exclude composite or even blends. They could achieve the same results, but they have to face a material which is now quite well perceived by the market. It is not too expensive, and it matches all the properties. And in particular, when it comes to composites and blends, I can see these issues or challenges. The transparency and the color can be a problem, especially the transparency. The refractive index of the material should match very well, and also the adhesion and the intimate adhesion between all the interfaces should be optimal. And the processing could also add some problems, especially could result maybe in higher costs, also associated to the raw materials. And I wouldn't exclude that for the future, composite can be combined with photopolymers. And this might be the question that some of you have in mind: why aren't aligners directly produced via 3D printing? And the main answer is that the property of most resins, especially metacrillate resins, are not good enough, both in terms of aesthetics, that they tend to have a not very nice finishing, and also are prone to staining, or also yellowish color. And stress relaxation, the ability to retain stress, it's really poor for most UV resins compared to thermoplastics. Toughness and fatigue resistance are also quite an issue. So I hope this gave an overview of our company and where there are some possibilities for composites and what are the challenges. And we're always looking for partners and novel solutions. Thank you.
Yeah, Thank you, Damiano, for this trip into dental applications. So now we will stay in Switzerland and go down the value chain. So please welcome Anatole Gilliot, CEO of the summit's main sponsor, Suprem. So Suprem is based in Switzerland and specialized in the development and manufacturing of continuous fiber reinforced thermoplastic materials for mainly automated processes, including tape winding, tape placement, 3D printing, and compression molding. Suprem offers tailored products for applications down the sea up to the space, including, of course, sports and medical materials. As such, Suprem is capable to scale from prototype up to large volume production. And Anatole is an engineer in material science. He also holds an executive MBA. He has a lot of experience, over 15 years, in fiber reinforced composite materials. He collected his experience at the DLR, at Airbus, to Tenax. Anatole, the stage is yours.
Thank you, Yannick. And hello to everybody still from Switzerland, now from Lausanne. I'm very pleased to be back for the third day. So yeah, Suprem is developing and manufacturing some plastic composite materials for different application. Yesterday I talked more about sports and leisure, and today I will talk about health and medical. The idea is to give you some example of materials being used or could be used. Suprem is ISO 13485 certified, sorry. And this is necessary to bring medical device on the market. But just to make it clear, we don't bring ourselves medical device on the market. This is a responsibility of customer, but they have requested us to be certified to that norm or standard. Oops, sorry. So today I will talk about two, I would say, main fields for health and medical. On one end, more out of body or part of the body. Yeah, we heard yesterday and the day before yesterday a very good presentation on orthopedics, and there will be one following after that. So these guys are the expert. I will just give you a flavor of what is possible with thermoplastic. And the other application is in the body. These are implants, and I will give you yeah, some example of application and how it can be done. So concerning out of part of the body, as we've heard, for prosthetics or orthopedics, stiffness and strength are important. Lightweight does help as well. In fact, it was less of a topic over the last days. And an important topic, point is fatigue, since this material or part has to withstand long-term flexion or sudden change of flexion. You could manufacture with thermoset, but I do believe there is an opportunity for thermoplastic material. You can get rid of the whole complexity of supply chain with freezing the thermoset resin. The shelf life, you have to use thermoset resin before making the part, so you can get rid complete of this. And you can automate your process. You can do by hand if you want, but you can lay down material in an automated way. In situ, so one step you consolidate, you lay and consolidate, or you can bring a second step by bring pressure afterwards in compression molding the part, and this can be done typically with tape material. On the other hand, as we've heard over the last days, there is room for new technology, especially 3D printing, where you could customize a part to the patient. And that is and should be, and hopefully will be possible with this technology. And in such a case, both tapes or profile or filament could be used to lay down the material. In the body, here again, stiffness strengths are needed. You need to have mechanical properties that are close to the body. Didn't do anything. The slides disappear, but it's not for me. Thank you, Cecile. And the idea is to replace typically titan. Titan is one of the main materials being used for implants in the body. So carbon composite, especially carbon peak, can be used for such an application. We have our sister company, Ecotech, which is our customer and sister company, manufactures such implants, and they are supplying in Europe and in the US. They are FDA certified. So you have on one hand the advantage of the radiolucent property of carbon peak material, and it is biocompatible. So it's inert carbon, and peak polymer are inert. So it's alive. My baby is coming in the room. So you have the tooth function that you have beyond the mechanical properties itself. The first part is a cage that they use in the backbone to replace damaged or broken bodies in the spine, and this one can be manufactured using compression molding, and certainly you have some machining to get the shape, the final shape of the part. And you can also bring some coating, typically titan coating, to enhance the bond to the tissue. So you can make that out of tape or even rod. Then you have the screw, which is also used in pedicle system. I will explain it a little bit more after that. That is also used in the back of the body to maintain the spine during operation. And here again, you can use compression molding and machining to manufacture the part. And finally, you have a very complex shape, which is also used to replace spiral bodies in the back, and that is also manufactured out of composite and carbon peak in this case. But this is a very complex part. I was quite amazed you can make something like this out of composite. A bit more details, especially on the pedicle system. So this is what you see here. It's composed of a screw, carbon peak screw, with what we call a tulip, made of titan. And you have here kind of a bar or rod that helps to maintain the screw toward the back of the spine. So here you have a radiograph of the spine, and here you can see the screw. So at the top of the screw, this is metallic. Then you have composite, so you don't see anymore. It's you don't see any kind of X-ray. And at the tip of the screw, you can see the screw again. So the advantage is that when you do such X-ray, the doctor can see what has happened, especially when you treat tumor. You could see how the tissue has been treated, and you can also plan future radiotherapy. So you know where you are in terms of treating the tumor. Yes, you won't see the carbon peak as mentioned. So sometimes that's a problem. That's why you bring some functionality into the composite. The tip of the screw, you have some marker, which allows you to see where is my screw in the body. So here's a specialty that we also offering. We can bring functional material into the composite material to allow such a detailed picture. Finally, I would like to thank JEC and to all of you for listening to me over the last 3 days. And I really send you lots and lots of fresh air from the Swiss Alps, because we all need it. We need to get out, we need to get some fresh air. That's the best thing we can have. And I'm looking forward to see you at JEC next year. Thank you.
Thank you, Anatol, for your insights. Very interesting what you are doing in the materials field. And of course, thank you to Suprem and JEC to make this event happen the last 3 days. So now we are going to move from Switzerland to Germany and up the value chain towards the human material interfaces. So I would like to welcome a well-known and premium brand in the medical tech products field, Ottobock, represented by Maximilian Segel and Johannes Wölper. Ottobock started over 100 years ago and became a global reference in its field. The goal here is of helping to restore mobility to people with disabilities and protect what mobility they have. And this stands behind each and every one of the company's products and services. More generally, it is about maximizing people's quality of life by allowing freedom and independence. Maximilian is an engineer with a solid background in the sporting goods and composites industry. And since 1994, he has been the lead person when it comes to composites materials and parts at Ottobock. Johannes started his career as a turner and pretty quickly decided to go back to university, where he became an engineer while developing skills in many exciting fields, including aerospace, composites, machine learning, and sustainability. From 2019, he applies his skills to further improve the living quality of Ottobock's customers. Maximilian, Johannes, the floor is yours.
Thank you, Yannick. Hello, everybody. So we will start our presentation with the short agenda, a little bit the history at Ottobock with materials, and then I hand over to Johannes. He tells us something about orthotics and prosthetics with CFRP materials, and then we gave you a short overview over the company Ottobock. So the next slide, please. Thank you. Ottobock, as you hear, is starting over 100 years ago with wooden prostheses. And after the Second World War, we was one of the first who has reinforced materials in our program, in our catalog. So they started with UP resin and some cotton and pelum reinforcements. And in the 90s, late 80s and 90s, they become more and more with glass fiber and acrylic system. So the acrylic system was first started in the early 1980s. So afterwards, please the next slide. Thank you. So the industrial production of products, Ottobock started in the early 1990s, and this was a knee frame for hydraulic knee. So that was the first steps for industrial production of prostheses. So there you see a lot of different products. That was mainly the key points for industrial production. Starting with the frame, then some foot constructions, and at least industrial manufacturing orthosis. There we see later on a little bit more. So I hand it over to Johannes with the detailed information. Thank you.
Yeah, thank you, Max, for the first part. I'd like to give you an overview why we are using CFRP in our products. So it's coming, as we already had in the introduction, from increasing the life quality of our customers by fulfilling the needs for what they use their products. And that is also the point where we start with, or where the big challenges come for us in general, so speaking in general, that our customers are all individuals and all are different. And that makes a wide range of needs we have to fulfill with our products. And that's one of the biggest challenge where we want to use CFRP to fulfill these needs. A further challenge here is that we have products in our lines where They are very specifically made just for one customer. So again, the diversity of customers, so lot size of one, but also have, as we already have seen, the industrialized products here. Further point here is the evolution was quite interesting. Was very good in putting a lot of function into a small space. So that's also a challenge for us that we want to replace or reproduce these functions in our products. Further point, maybe a lot of people of you already know if they took a look at their smartphones or smartwatches and counting the steps along the day, and you know what what fatigue loads we have, for example, especially for our leg prosthetics and orthotics, that we have to produce our products that they fulfill their function along their life cycle. And also, we have some regulations to fulfill to produce safe products for our customers. And for this, all challenges, we try to use, if possible, or if makes sense, we try to use CFRP to fulfill these challenges and therefore fulfill the needs of our customers. And the next, I want to show you some examples. Now, first, I want to show you the advantage of CFRP, which we are using in our products, and afterwards I will show some of our products where we use these advantages. So thin word structures and lightweight design are two things which come quite together. So we don't want bulky parts, so that it's easy be wearable with normal clothes and shoes. Lightweight design, because you carry your product around all the day. Freeform shape, it's also about, you can connect it to or adapt it to the body of the specific user. Specific strength means here for me that it's able to store and release energy during the use. Stiff or flexible, that's the general point of CFRP, that you find the right layup for the specific use or the needs in that specific area of a part. Long fatigue life in general, and also connected with the point that we don't have a loss of stiffness along the product life. And also, maybe not the main selecting criteria for CFRP to fulfill these challenges, is the high-tech optic of some products. So if we're using CFRP in some parts, we also want to show it. Good. The first example I want to show you is Genium Black, just as an example for the frames we have in product for these knee prosthetics. There we have the point that we need a very stiff frame to carry the load of the body. And for this, we have quite a free-form shapes that look very slim and don't look bulky below normal shorts, for example. And here we are using specifically stiffening along specific areas, so place the layup. And that way we need where we need the stiffness and where we don't need them. But what we also have here is that we are using metallic inlays, because we have some rotating axis in here, which providing the mechanism of the knee. And for this, we have to also cope with the problems of metallic inlays here. Also, and going towards the foot now, we have a metallic inlay on the lower end to provide a secure clamping towards the foot. As mentioned, coming from from top to bottom, now I want to take a look at the foot prosthetics we have in program, or some examples. On the one side, on the left side, you see more for the everyday use. On the right side, it's for the sporting. But both together definitely need these effects, as I just mentioned, of the specific strength. So they are able to store energy and release it during the walking process. That's the main feature why CFRP is so much in use in this product types. But also, which is here relevant, is that's lightweight for all-day carry, but also the free-form shape, because especially the combination of the material properties and the shape of the springs bring together the functionality of these parts. What is quite nice and beautiful to see is that we allow people to make records with this, athletes who make extraordinary records and results during sporting events with our products. But that's not in general the point. So what's about is that we have a lot of people behind this. So that's these athletes are just the tip of the iceberg, which are able to do something. But we also have a lot of people doing their regular day marathon, as I just wrote here, but also doing just recreational sports with these prosthetics. So be able to do this is for the life quality change. So furthermore, last product, which is now orthotic. This is if you have, for example, a stroke and not able to lift your foot anymore, this product is helping you, this walk-on. Here we have a lot of functionalities of CFRP, which we are using here to create this product that's thin walled, because it should stay below your normal clothing and should fit into a normal shoe. Lightweight, yeah, carrying it around all the day. Freeform, you can see it's very wrapped around the body or around the leg. So we're using this freeform functionality of CFRP here as well. There is a spring included in this component, so the specific strength is overused. And yeah, we use different types of layup in the structure along the spring to create the specific needs we have at the specific areas. And fatigue, as well already mentioned, is also a big point here. In general, my opinion is there is not bad material, there's only the bad use of a material. So we try to use CFRP in that areas where it makes sense to fulfill yeah, our plan to provide more life quality for our customers. Good, I hand over back to Max for some short presentation of our company.
Thank you, Johannes. So, who is Ottobock? So we are global, all over the world. So we have more than 180 patient care centers. We are about 7,500 people worldwide. And we are in 58 countries. So that's a great deal for us that we are all over the world and have the informations in which countries, in which areas, which needs are. So our sales are roughly 1 billion euros. So we hope we hold it in this year. It looks good. So the next, please. There. So where we are have our production. So especially for laminates for CFRP and fiber reinforced plastics, we are located in Salt Lake City, where we have the foot production. We are producing laminates in China. They're mainly made the orthosis you see in the pictures before. And our development and all the possibilities of manufacturing are located here in Duderstadt. So that's the reason we could make our developments with fiber reinforced materials here in Duderstadt and in Salt Lake, and our shop floor is in China. And they are fully connected, so every area can produce the same products. So next slide, please. Thank you. So that's the end of the presentation. Hopefully a little overview over Ottobock. Thank you very much.
Thank you as well.
So Maximilian, Johannes, thank you so much for demonstrating how composite materials have a role in enhancing people's quality of life. Last but not least for this session, I would like to introduce Matthew Dickinson from University of Central Lancashire with a great topic inspired by a young woman. More about it later. Dr. Dickinson's research interests are focused within the world of wearable technologies to aid in assistive or rehabilitative applications. By using computational computing software and the latest in cost-effective manufacturing, he is aiming to develop new tech that is combining low cost and maximum function. He is also a subcommittee chair of the ASTM for exoskeleton standards, where he works with companies such as Ford through to Mawashi Science and Technology on the standards for this technology in general. Matthew, I'm really excited about your presentation. The floor is yours.
Thank you, Yannick. Yes, I'm just going to give you a short presentation. I hope you can understand that everything that I'm about to show you is a very summarized process of what we've been doing. This project is very close to my heart and it's extremely exciting. So I won't hold up any longer. I will get moving forwards. So when I was first introduced to the aging population, I won't lie, at first I'd first seen this and thought, I'm not sure exactly what this is referring to, but I'm hoping that with this I can give you a brief introduction as to what this is about. So this is quite a famous image, which was published by the Centre for Aging Better, and it shows at the moment the age population in 2015. As you can see there, between 10 to just less than 30% were aged around 60 years or older. As we get close towards 2050, what you can see there is that growth in the 60 and above of 30% or more. You can see it becoming much larger. Now, I'm just as bad as many in the past. I looked and thought, well, what really does that do? How does that really affect everything on the bigger scale? Now, I'm often not the biggest fan of having millions, having lots of writing on a slide, but I have been just as guilty this time. It's estimated, well, the Centre for Aging Better, they estimated that 1 million people have left the labour market at the moment due to health conditions. Now, granted, these won't be necessarily to do with muscular breakdown or any type of muscular-based problems, but a large percentage of this is directly accredited to that. Now, they also go on to publish even more interesting data. Now, this is what really captures my thoughts, really, of that men aged at 65 can expect 19 years, roughly around 19 years of extra life. 10% of them men will be of good health. The rest will need assistance, they will need medical care. And when it comes to women, women are a little bit higher. They can expect around 21 years, roughly around 21 years more once they're at the age of 65. And you'll find more of 11% of these women above that age will be of good health, but only 11%. And more alarmingly, it is forecast that once we start to get into a more higher level of aged population, with these important facts behind it, what it actually suggests is that there will have to be a healthcare spending that will rise at around 3.3% to 3.9% consecutively year on year to try and keep up with the demand of more and more people becoming and needing the all-important help. Now, at the left, I've just tried to give an overall view of different ways of tackling the aging population problem. Now, this, personally, this really grows nicely into what I'm going to discuss. We focus more along the lines of the use of technology. We focus more along the lines of more of assistive technology. And as Yannick alluded to, this project was initially initialized by a very young woman, a 15-year-old young lady. And that's another story, but it's a fascinating topic where all this came from. But to come back more in line, what we started to do at the university is we started to look at exoskeleton technology. Now, this is really interesting. Originally, when we designed this, we were focusing all our efforts around children. It was about the aid and assistance of children in need of rehabilitation, in need of assistive technologies, because from an all range of different types of muscular deficiencies through to injuries, that children need that help just as much as anybody else do. Now, this exoskeleton tech is purely based on the rehabilitation side or muscular deficiencies. It's not focused on the paraplegic approach. So the reason that is that, as some of you will well know, that as a design process is something else completely. It's a whole new process that needs to be addressed. So what we've done is we've focused around that assistive element. So there is muscular activity, as weak or as great as it might be. Now, in this process, I'd originally, now the segments I'd originally proposed that we could have produced this out of an aluminium structure. And then we started to look at it, and we just thought, this is madness. Why would we do something so heavy? Because the weight of this was vital. If a child was going to wear this and we were going to sculpt this to become force, how could we even look at that? So we knew that this was not going to be a low-cost assistive methodology. We then thought, you know what, let's just print it. Let's just take some standard polylactic acid, some PLA off the shelf and started printing, and we printed it. Interestingly, we found some fascinating results. We found that the polylactic acid was actually active. It could support the body better than we ever imagined. It had so much potential behind it. Now, this system itself uses linear actuators. I know quite large, quite bulky, but it uses linear actuators. And the way that this thing functions is, you'll notice if you look directly actually at the design, you have white segments. This is the representation of the PLA. The black markers that attach actually on the drawing or on to the left, you'll see it in white. This is actually made of a thermoplastic, the PET-C, and it's PET with carbon integrated within it. And this is a composite material, is a phenomenally performing material. We knew that we needed something that could support the conversion of linear force through to a moment. Because what's important with this is if we attach a linear actuator straight to the back, as it begins to push, it'll essentially drive into the body, and in theory causing more damage to the user than anything else. So what we did is we made these custom caps, if you will, and this was a motor to skeletal interface. What we wanted it to do is at the lower end of the black marker, let's call it, is a nitrile structure. And the idea is as the linear actuator pushes, it will convert that vector into a moment. In essence, pushing the back, like as if somebody was pushing your back. And what we've then done is we'd realized that it was perfect for us to being able to support the body. We realized that what it would actually do is it would actually drop in costing. We noticed all types of different things that came out from it. What we did know is if we were going to design for children to actually wear this device, it needed to be able to grow. One of the biggest issues with these devices is if a child puts it on, if they outgrow it, in one hand you've given them mobility, in the other hand it's been taken away. So what we wanted to do is to introduce a device that even parents could maintain. Now we use what we nickname the continuum method. So it looks like a spine. Now the idea is if there is maintenance needed, one of the spinal segments can be removed and a new one to replace its counterpart. So making it extremely accessible and meaning that the maintenance of this can be done at home or by a clinician, which is our real main aim for it. In the center of this, we have a nitrile structure to allow that body to flex and move. And we've been experimenting a little bit more. I'll allude to this a bit further down, but we've experimented on the use of electromyography. And we've been, at the moment, had some amazing success. We've been able to characterize particular muscle groups, and we're able to get a very similar motion with that. But anyway, let me just move on to the next slide, because I apologize, I get so excited about this topic, I could go forever about it. So what we did is we produced it, we simulated it, we went through as many different techniques, and what we were really trying to answer with this is, could PLA as a base part material actually support the body like we claimed it could? So we built test rigs, and we looked at the neck actually as it was being actuated. We built replica pieces, we manually calculated this, and then we moved to the trunk section of the spine as well. Now you'll notice on it, there's actually, if you consider where all the actuators hit or touch, let's say, these are key active points. Now the spinal segments in between are passive. Now this has proven to us to be a little bit of a questionable state. So even though we know this will work, we knew that we may need to reconsider a further design. Now, as we move forward with this, we realized also that this is polylactic acid. The issue with polylactic acid is it can easily grow polylactic bacteria. So we approached Tinius Olsen. Tinius Olsen have been a phenomenal support for us, and we are now moving towards using a copper-based nanoparticle polylactic acid, which the company themselves are called Copper 3D, and we've been looking at their material to actually act as the ideal solution, because the biggest problem with this, our present option, is that it needs to be cleaned. If we put this through a cleaning process, we could probably have further damage. So with the aid of Tinius Olsen, with the aid of some of the amazing people that they've really been able to help us get to the next phase of our next design. Now, from learning what we've presently done, we have some really exciting design ready to be released, but we need to just make sure that the material that we're using is going to support 100% to our claims. So let me just finish, because I appreciate I can go on a little bit. Let me just finish by saying, by some of the findings that we've found so far, we know polylactic acid will support in an equivalent representation of what can be a counterpart metallic component. We know that by doing that, we can drop the price of maintenance of these components by at least a factor of 10. Each one of these components on here, granted, I did spend, I bought a few times, so each one of these components maxes out at around £1 single per component, and this makes it accessible for all families. Further work from here, we're aiming to further go down the line and studying the antimicrobial resistant PLA material. Again, this is all from the help from Tinius Olsen, who they've actually lent us one of their high performing machines to actually be able to really dive as deep as possible into that. Again, the mechanical testing relates to the material itself and the human machine interface. One thing we realized is if children do wear this machine, it is too big. We weren't happy with it being so big. We wanted to make it more conservative, if you will, more discreet, because if anybody wears it, we want them to feel comfortable in it. The biggest finding we've got, the performance of this material doesn't just refer to children. We now know that it will refer to adults. We can refer to anybody who has muscular deficiencies or needs in rehabilitation. So a simple idea of what we thought was with children has turned into something absolutely massive, and that's me. So let me just say thank you for listening, and I'd like to just acknowledge again Tinius Olsen and the people I've been working with. And thank you again.
Matthew, what a journey. Thank you. So now please stay with us while Damiano, Anatol, Maximilian, and Johannes come back on stage. And I will now move into the Q&A session. We have quite interesting questions here from the participants. So I will take the most voted question, which is from Mario Saba. And the question will go to Anatol first, and the other one, feel free to just intervene also. It's when would a doctor recommend a carbon peak part versus a titanium part? Is it the age, the fatigue life, the size, or other parameters?
To my knowledge, it's not linked to any of this, so age, fatigue, or size. And there was two cases. There was you can use carbon peak instead of titan for plate for trauma, for broken bones. There the advantage is not so tremendous. It got lighter, but probably half of the doctors say I don't care. But for the screw, for the treatment of tumor in the spine, there is two advantages. The first is sure it's radiolucent on one hand, which means when you treat the tumor with radiation, it won't diffract as it will be with titanium screw. Titanium screw will diffract the beam, and then the treatment of the tumor itself will not be as efficient as it would be with carbon peak. That's a big advantage. So you can reduce the amount of treatment or radiotherapy you're conducting. And the other one is the fact that you don't see the screw, which is good or bad, depends, as I mentioned. So you can see what happened to the body after the treatment. And this will be more difficult with a metallic screw.
Okay. Yes, thank you, Anatol. Now, question is for Damiano. So it's a question by Pascal Joubert Desouches. So do you take care of 3D printing polymer orientation lines to secure isotropy and impact strength?
So yeah, this is something that it's definitely something that we look into. It's not the only thing though, and it also depends on the product. Some are not really, it's not really relevant as long as the printing is optimized. For some products that are not subject to high loads or impact, we don't look into that. Especially this one, the models that are used to. So I don't know exactly to what product Pascal is talking about, but the clear aligner is made on this. And here what is more critical is the lines, the printing lines. And this can be then reflected on the surface of the aligner that is formed on it. So it's more a balance of having a smooth surface and at the same time very accurate, because this has to resemble as much as possible the dimensions of the patient. So it's really a balance, but it's something that if you're ever going to directly print a clear aligner, this is something that we need to consider, and we are considering when we evaluate material. We print them in different directions when we test them in fatigue or fracture toughness.
Okay. Thank you, Damiano.
You're welcome.
Now, question, I see that Johannes is already writing the answer, but we'll take the question from Pascal again about the impact toughness of the material you are using.
Yeah, the impact toughness has an impact on the selection of the material, especially for the knees. There is a knee drop test, which has to be fulfilled by our products. For the foots, it's more due to their flexibility. It's not that relevant. Maybe Max, I haven't been involved in a development of knee so far, so maybe additional information from you, or?
At all, the impact is not the main thing we have a look on. So maybe impact is important for containers where the stump inside, but it's not a main view in development of this.
Okay, Thank you, Max. Thank you, Johannes. And maybe to close the Q&A session, a more general question to the round, and just feel free to answer. It's more related basically on innovation, because obviously many of the current challenges which we have seen during the summit, it will be overcome hopefully through major innovation. And what would you recommend when it comes to making future generations more innovative in terms of education also? Maybe Matthew, you want to start?
Yeah, reflecting for positivity through innovation. I think now to give you just a brief outline to the skeleton project that we've been working on. This all started from a public engagement event, an outreach event to schools, where a question went to all children in a school and said, if you were going to solve a problem in the world, how would you solve it? And a young 15-year-old lady wrote down, why is there not a special shirt that children can wear that can help them move when they've got muscular problems? And I thought, there must be millions of these. And she was right. There's not a lot out there because children grow. And I think problems like that, I think speaking to kids and just getting them involved in this way, I think is amazing. I think it's really amazing thing.
Thank you. Anybody of the speakers would like to?
I would. Oh,
Go ahead.
Okay, yeah, I couldn't agree more, because children don't have our already taken perspectives on some stuff, so they are totally free in their mind and don't have seen maybe a lot of things. The other point is, for me, we are looking quite often is nature, because evolution was quite creative about doing a lot of things. So using this as an input and trying to use this for some products is also, I think, a good point where you get ideas for new ideas.
I was saying that I also agree, reaching out to kids when they are already very, very young, very small. I think it's a way to go into schools and talk to kids. And I also agree that they have fresh minds. They are not biased from the outer world. And also what I would do is to reach out to kids, because maybe not all kids are lucky enough to have parents who are educated enough, or that provide even if they're not highly educated, that provide the means for these kids to think in an innovative way, think about the future, technology, challenges. I think maybe it's the school and society that should have a specific attention to those kids, not leave them behind.
Thank you very much for all your opinions and answers. So obviously we could keep speaking for a while on such exciting topics, but time is flying. It's already 5:15 and the business meetings will start. So at this point, I would like to thank you all for attending, for speaking, and again, thanking also Suprem to make this possible by being the main sponsor. So business meetings will take place from now on until 5:40 p.m. And afterward, feel free to join us again for the starter pitches to close both the day and the summit. Enjoy and see you later.
Thank you, Yannick.
Thank you very much to everyone.
Okay, bye.
Bye.
Bye.